A novel AI-ML regression flow for SoC verification. Chapter 1 Abstract. As developing the chip design and verification goes hand in hand to meet the time to market, every new feature implemented may cause failure to already passing tests. So the common reasons could be change in test bench, design and simulation environment. Our turnaround time to debug a failing simulation in regression may take around a week time due to the manual effort involved in debug and small simulations. As for analysis, overall verification effort can take up to 65% of a whole design cycle, especially debug would take more than 50% of the verification effort. So until a few years ago, there was no legitimate solution in the market which used intelligence enough to help reduce laborious and time-consuming steps in the verification domain. Of late, AI is as sensational in semiconductor sector, enhanced design and verification, and back-end processor and fostering innovation. AI plays an important role in SoC verification as the design size is huge and the simulation time are considerably large. The turnaround time to debug a failure may take a week of time. In regression suite of around 10,000 tests, it's gonna be take many days by many engineers to debug failure, as engineers would debug one after another failures. We have come up with a novel flow using the AI-ML to analyze the failure signature with a historical database and provide a possible root cause analysis in the deep cycle. This flow consists of three main AI-ML engines called CodeMiner, WaveMiner, and Defect Tracking Tool, DTT. Each one contributed to reduce time in various possible debug cases like repeated failure, new feature. As this flow can be applied on a multiple failure in parallel, so overall debug time for regression can be reduced by around 10 to 20 folds based on the complexity of the design. This flow is adaptable to AIP subsystem and associated environment, which is based on incremental design DB flow process. Chapter 2 Introduction. Semiconductors are an integral part of the all modern electronics, from smartphone to the home appliance to complex computing systems. A chip design becomes more complex by size and functionality. Traditional methods are sufficient to meet time to market targets. And the development process of a chip verification effort is pretty high compared to a design and subsequent steps. Any idea that helps to reduce verification effort would eventually help reduce the overall chip design cycle. The ultimate goal of the verification is to find both and faster reach coverage target in the shortened duration and to meet product roadmap time to market. Figure 1. Conventional verification flow. To discuss more on the verification stages, following are the steps involved in verification flow: verification planning and review, and test bench development and coding. Running simulation, failures debugging and analysis. Review the metric coverage, functional coverage, and test to pass rate. In above steps, 70% of the time takes debug and analysis. Although above steps remain same across IP, subsystem, SoC verification, debug and analysis steps, and plays a crucial role in SoC as the simulation SoC design and verification, as the simulation duration is pretty larger than that of the IP subsystem. Hence, debugging and fix time for each failure would be manifolds larger than IPN subsystems. In above verification steps, some steps are backed up by tools to reduce the turnaround time. For example, WaveManager tools helps in developing the verification plan faster, while dbt VS Code can help in understanding and developing tests faster. Unfortunately, debug process is always manual right from the evolution of the chip industry. The area of focus in this paper target to address the same by utilizing AI-ML techniques to reduce simulation debug time, hence reduces the overall turnaround time of SoC verification. Operate artificial intelligence is applied across the many applications, platforms, and industry. For example, AI-based home security cameras, traffic monitor system, home appliance, and etc. Even in semiconductor domain, AI can find its own way to help improve quality and turnaround time, especially applying the AI-ML yields better results in the verification as it takes pretty large percentage of the overall chip cycle. Though chip design and verification domain was anticipated for AI, while it started a few years back, of late chip design has been in focus. AI-ML is being considered for specification to design from design to verification, from verification to physical design until to the chip tape-out. If AI can help us generate simulation results faster, engineers can focus on debug and find out more bugs. In SoC verification, numerous tests are supposed to be run to cover each and every block and it's across the communication channels. With the conventional method, it's difficult to debug all failures in a given time as the simulation times are pretty large. Common issues may appear across multiple block level simulation. Hence, there needs a technique by which common issues and its resolutions are shared across blocks and end-to-end scenarios. In this case, ML techniques provide a promising approach that is required to learn from past debug resolutions and apply to latest regulation failures. Since the last few years, many EDA companies have been working with AI/ML, and some of the tools flows have been making rounds in the market. Verisium is one of the such a success tool. The Verisium platform is a suite of applications leveraging the big data and generative AI to optimize verification workloads, boost coverage, and accelerate root cause analysis of design bugs on complex SoCs. Verisium platform uses AI on log files, RTL, and test bench churn, and division control and waveforms to accelerate and assist debugging and reducing manual effort by up to 32 times. Verisium accelerated the root cause of analysis of design bugs, boosts coverage, and optimizes verification compute to farm resources for SoC complex SoCs. Verisium's CodeMiner reduces the debug time by identifying the RTL logic that could be culprit for failures. Verisium WaveMiner helps in finding root cause by comparing design waveform of the pass and pass-fail cases. These two applications can achieve the remarkable improvement in efficiency. In-house tool called defect tracking tool (DTT) is an ML solution which mines the data from the simulation log, Jira bug tracking information, failure report from the old project. This tool consists of three applications: Abnormal Simulation Detector (ASD), which is based on data from the multiple linear regressions to make expected at runtime. Debug History Finder (DHF) is a pattern matching technique that is based on a Leblanc distance algorithm to calculate similarity between their errors. Last one, Debug Guide System (DGS) is based on the algorithm BERT, BRT, XLNet, and Random Forest to categorize the simulation errors in 10 different categories. Chapter 3, Literature Survey. In this survey, we provide a comprehensive investigation of literature by examining how AI/ML is utilized to enhance the chip development process, especially in SoC verification debug time. Although AI is not new to software domain, it's relatively new to chip design. Renowned EDA companies have been working on AI/ML application for quite some time, but the products are available to users only after 5 years. To name some of them, Verisium platform by the Cadence design system. Synopsys.ai is a suite of AI applications by Synopsys Incorporation. There are used to be some techniques to speed up the debug time of verification. Some of them are auto-X detection and fast root cause analysis, covering based on the ranking to reduce regression time, but those solutions are based on the current data and the simulation information. It doesn't consider past data and the learning experience taken into consideration. Afraid, ED companies have invented AI solutions that take us into account of the previous pass or fail information and compare against the current simulation. It does mining of the both snapshots and figure out the root cause. These techniques can apply to a final test bench issues as well as the tools as a business secret, though much information is disclosed at vendors. To find a correlation of the simulation failures, but the algorithm is used to DTT tools, and the first step in this process is to classify the failures signature. The test classification is the subfield of the ML that discusses about classifying the test into different categories. It's commonly used as supervised learning techniques, which means the algorithm is trained on a set of tests that already have been labeled and with their respective categories. Once it's been trained on this data, the algorithm can use what it's run to make a prediction about new unlabeled text. The algorithm looks patterns into a text to determine which categories it belongs to. Chapter 4 is problem definition. As described in the introduction, regression debug is challenging and time-consuming task in verification due to the used simulation time in SoC as it's large in design, complex in logic, as the features are still under development. Any new addition to or update, like adding new IP, enhancing the IP, adding the new features can done until last stage of verification, as such update would cause a failure in already past simulations. Engineers may have to spend time in debug again through the same test was passed in previous tag. Note that debug is a manual task that involves in generating the waveforms, rerun, and pull out the required signals, trace drivers, until root causes are identified. This is an efficient way of the verification. Hence, we come up with an AI-ML flow to accelerate debug task, hence reduce turnaround time of verification. 5. The proposed AI-ML flow. The primary goals of using AI techniques to reduce technologies are to reduce cost, save time, improve quality. The purpose of flow of is going to address in reducing debug time, hence the accelerator of the OSS verification. This flow is intelligent, scalable, and adaptable that can fulfill the following motivations. Reduce or avoid the debug time, find out the root cause, reducing overall the turnaround time of debug, scalable to IP, subsystem, SoC, adaptable to various products. So the proposed flow is based on the three AI-ML flows. One solution called DTT is an in-house tool, while other two are from the Cadence on the Verisium platform, CodeMiner and WaveMiner from Cadence. The Verisium platform is a suite of applications leveraging big data and generative AI to optimize verification workloads, discovery and accelerate root cause analysis of design bugs on complex SoCs. Verisium CodeMiner provides algorithms solution to compare multiple source code revisions of the AP on IP or SoC, classify these revisions, and rank which updates are most disruptive to the system's behavior to help pinpoint potential bug hotspots. Verisium WaveMiner applies powerful AI engines to analyze the waveform across the full verification test suite and determine which signals at which times are most likely to represent the root cause of the test failures. As described in the introduction, defect tracking tool DTT as an in-house tool is an ML solution that registers the failing information along with the solution. If the same error is encountered by other user, it displays the solution to be applied. The figure 2 depicts the flow diagram involving building blocks of a proposed AI-ML flow. In SOC verification, as engineers have to work on developing new features alongside, the new involved three phases called planning, execution, and debug. In the planning phase, the test plan consists of n number of tests, each passing status and corresponding tag in which it passed for the first time. In the execution phase, regression is run as per the verification strategy and the results are published. Each notice that test T2 has failed in the latest regression on tag N+1. The same test got passed in tag N+N-1 and the debug phase. T2 is gonna debug by using AI-ML debugger, the leverage 3 application called defect tracking tool, DTT in-house tool. The CodeMiner Verisium app, WaveMiner Verisium app, as once failure is fixed, pass tag is updated in ML database. Figure 2 is block diagram of this AI-ML flow. Planning, execution, debug. The figure 3 explains the flow and steps involved in the failure debug. 1. Regression manager launches the regression of tag N+1. If the test is passed, current tag is updated in ML-based. If the simulation has a failure, the following cases are analyzed. If it is old or known failure for which TTT has a solution registers, the same get applied without a user invention and given return. And if it's new failure, it can be all together new test without any past history, or it got passed in the old tag, or encountered a new error signature. Failure with history. This is debugged with the help of WaveMiner that generate waveform, wave dump, and compare the signals at each time, even and find the root cause. And failure with no history is gonna be debugged by the CodeMiner that compared after snapshot of the previous tag and current tag to help localize the issues and provide a possible root causes ranking order. And then the user has to embark to do the further debug to find out the exact root cause. In any case, once test is fixed, tag is updated in ML database. AI-ML service builds attractive result if the number of the failures are more. In traditional method, the debug process is manual and iterative, and the debug TAT becomes exponential, the number of failures increase. And the AI-ML debug process, many steps in the debug cycle is automated in regression flow. RC of the all failures gets interest generated without manual intervention as described in Figure 4. Figure 3 is the flow chart of AI-ML debug. Figure 4 is the traditional AI-ML debug approach. Chapter 6 is applications. This methodology can be applied at various verification approaches as mentioned below. Debug multiple failures simultaneously. Easy deployment of across any DB flow is adapted to the IP SoC subsystem levels. Debug multiple failures simultaneously. Assume there are multiple failures one user has to debug. In conventional way of debug, user will debug one by one in sequential manner. Hence, the overall debug time of the project is tremendously large. If the AI-ML flow is applied, failures are debugged in parallel. If requires number of licenses available. Hence, the overall turnaround time of the debug of the project gets reduced by the manifold. It's observed that overall savings that AI-ML flow is 20 times faster than a conventional debug. Easy deployment across the other DB flow. AI-ML flow can be applied across the various DB flows like IP, subsystem, and SoC. Time taken to generate a snapshot in the code WaveMiner results are very quick in case of IP due to its small design size which improves TAT. Whereas for SoC, due to its heavy size, snapshot creating and mining would be little slower compared to IP. adaptable to IP SoC subsystem level. This AI-ML flow is based on the RTL and TV code, which involve the CodeMiner and WaveMiner. CodeMiner is used to correct the RTL code automatically, which are causing the failure without a manual intervention. Similarly, the WaveMiner also fixed the bugs which are repetitive. This will improve the TAT and reduce the manual effort, and tons can be applied easier from the IP to SoC level without any difficulty. The success result. In this section, test bench simulation environment explained in detail like test access complexity, followed by improvement in simulation debug times using AI-ML flow. Flow test plan. We have considered two categories of the tests. First one is the basic scenarios like register programming connectivity check. Other one is the complex test, like core scenarios involving multiple transaction. For the example, access the DRAM back-to-back, initiating the camera to the stem to capture pictures in a processing imaging signal processor complex test. These two categories of the tests are asked to debug manually by junior engineer with less than 5 years of experience, a senior engineer over 10 years, and a new joiner with around 7 years of experience. Each one of them are asked to be debug the same test. The same is repeated for multiple tests in each category of test. Debug time comparison. Considering the above plan, we have collected the debug time for each class. Gain in overall regulation is as high as 20 times gain due to the reason that this flow can debug failures simultaneously, whereas engineer has to debug one after another. Result are details in the table 1 and 2 below. Table 1 is simulation turnaround time. Table 2 is simulation turnaround time is TAT metric, and again over the traditional approach. So the chapter 8 is future scope. The future of the AI in the semiconductor industry is promising. As technology continues to evolve, we can expect more sophisticated AI applications to emerge. Our flow will get equipment with a new application called the DV chatbot. It does provide not only value information to code or the debug faster, also helps engineers to learn more about the logic and functionality for each feature. As like a general chatbot, this app contains reference to the document, lists frequently called issues, and steps involved to achieve the task. A user guide commonly used task and so on. And then chapter 9 conclusion. Employing the AI-ML flow for the debug the failure using a data set of the previous regression task simulation results present a promise in the approaching the enhanced the efficiency and effectiveness of debug process in hardware design verification. It assuredly debug of the old or a known failure is avoided, and a user can focus on real RTL bugs instead of reinventing the wheel. The flow does accelerate verification cycles by leveraging the industry standard AI-ML application to reduce the time of the debug is scalable along across the various DV domains ranging from the IP SoC. Okay, today I read this paper, the Novel AI-ML Regression Flow for SoC verification from the DVCON2025. So thank you for your time. See you next time.